Calculus studies functions, and this course is no exception. We're going to be studying functions in this course. Right? Functions like f of x, or the sine function, or the square root function. And that raises the question, what are functions? If we're going to be studying functions, we should know what they are. And that question's pretty metaphysical. I mean, what are numbers? What's the number 4? I mean, that question doesn't make a lot of sense, does it? I mean, it's not like the number 4 is a physical object that I can go look at it and see if it's got polka dots or it's striped or something, right? But I know 4 objects when I see them, right? I sort of understand what numbers do more than what they are in some metaphysical sense. The same is true about functions, right? I'm not really going to tell you what a function is. What I'm going to tell you is what a function does. This is what a function does. A function assigns to each number in its domain another number. Now, this definition doesn't say anything about how the function does that assignment. Let's see an example. Just make up some example. Suppose I've got some function, I'll call it f for function. Maybe this function assigns to the number 2 the number 4. So I'll write f of 2 is 4, or f of 3 is 9, or f of 4 is 16, or f of 5 is 25. I'm just making this up. This is some function, and I'm telling you what number it assigns to each number, right? F assigns to the number 2 the number 4. F of 3 is 9, right? So f assigns to the number 3 the number 9. But look, I'm not just going to list off every single assignment that f makes. So instead, one way to talk about these assignments is to use a rule, like f of x equals x squared. And this single rule explains how all of these assignments are made, right? This rule says that f assigns to the number x squared. So in particular, f assigns to the number 5 squared, 25. Or f assigns to the number 4 squared, which is 16. Or f assigns to the number 3 squared, which is 9, right? So a lot of times, when you actually want to talk about how these assignments are being made, you use some sort of rule like this. And you write f of x is something to compute the output value. Right? So a function assigns to each number in its domain another number. One way to do that is with a rule. Of course, this definition of function involves another word, domain. What is a domain? Unless I say otherwise, the domain consists of all numbers for which the rule makes sense. Right? A function assigns to each number in its domain another number. And the domain is just the numbers that I can plug in. Now let's take a look to see what I mean by this. Suppose I've got a function f of x equals 1 over x. So that's a function given by a rule. It takes an input x and produces the output 1 over x. Right? It assigns to the number x the number 1 over x. But this rule doesn't always make sense, right? I'm dividing by x. Right? And to divide by x, what do I need? Well, I must have that x is not 0. I'm not permitted to divide by 0. So I can plug in any number for x except for 0. And that's when this rule makes sense. So I'll summarize that by saying that the domain of f is all real numbers except 0. So a function takes some input and produces some output. That's what it does. But how is it supposed to make us feel? How are we supposed to imagine that? Well, here's one metaphor that you could use to try to think about what a function is actually doing. Right? You could imagine a conveyor belt with the function, and you could imagine the numbers coming in, boom, being hit by the function, and then going out, transformed somehow by whatever the rule is of the function. This is what I'm talking about. I've got a conveyor belt here. I've got this big box. I'm imagining that big box is the function. And then here I've got the input. I'm imagining the number 5. Let's tell you what this machine is going to do. Maybe this is the function f of x equals x squared plus x. And I've got this number 5 here. And I'll start the conveyor belt going, so the number 5 starts moving through the machine. And when the machine is done processing it, it comes out from the other side, and now it's the number 30. Right? Because f of 5 is 5 squared plus 5, which is 25 plus 5, which is 30. So we've seen how you can write down a function by using a rule involving these mathematical symbols, right? X squared plus x. You can also write down a function just using English words. So let's see an example of that. Just make up a new function here. I'll call it r of x. And I'll define r of x to be thrice, that means 3 times, thrice the square root of x. And here I've computed some values of the function. Like the function at 4 is 6. Well, why is that? Well, r of 4 would be 3 times the square root of 4, which is 3 times 2, which is 6. Okay, now, of course, when I do the calculation this way, it's not too surprising that instead of writing this out in words, thrice the square root of x, I could have just written 3 times the square root of x. So maybe you're not too impressed with this. The point is that you can define a function just by writing down what the function is supposed to do using English words. So we've seen an example of a function that we define just in terms of algebra, f of x equaled x squared plus x. We've also seen an example of a function that I defined entirely with just English words. We can kind of combine those two things, right? We can use the English to sort of pick out different kinds of algebra. Well, let's see an example of that now. So here's another function I just made up. G of x is x squared if x is bigger than or equal to 5, and twice x if x is less than 5. The point here is that I'm using just a little bit of English, this word if, in order to select, based on how big x is, a different algebraic rule for calculating the function. This is a little abstract. Let me just do some calculations, and that might convince you, how this notation, this so-called piecewise notation, works. So what is g of 1? Well, let's take a look. 1 is less than 5, so that means I use the second rule for calculating g. So it's 2 times 1, which is 2. What's g of, say, 4? Well, 4 is still less than 5, so I use the second rule again, twice the input, 2 times 4, and that means the output's 8. But what's, say, g of 5? Ooh, 5 is not less than 5. 5 is greater than or equal to 5. So this if is telling me to use the first of the 2 rules for calculating g, so I'm going to use 5 squared as the output, and that'll be 25. Or g of 10, well, 10 is definitely bigger than or equal to 5. 10 is bigger than 5. So I again use the first rule, and the output to this function is computed as 10 squared, or 100. So this is really more complicated than just using some algebra, right? I'm using these if statements to select which of these 2 rules g will use to compute its output. In principle, functions can be really complicated. All of the examples we've seen are just doing various kinds of algebra. Maybe different algebra depending upon which values of x I'm plugging in, but it's all, adding, subtracting, multiplying, dividing, that sort of thing. But you can do really complicated things with functions. Let's see an example of something that's, really different than just doing, straight up algebra. Here's a much crazier example. Right? C of x is the number of even digits in the number x when x is a whole number, and it's 0 if x isn't a whole number, so otherwise. This is a really different kind of crazy function, right? So C of, say, 7,236 is 2. Well, why is that? This is a whole number, so I use the first part of the rule, and the number of even digits in this number, I count them. That's odd, even, so 2 and 6 are the 2 even digits, so the value of that function is 2. Or let's take a look at this number here, 60,202. That, again, is a whole number. So the value of the function at 60,202 is the number of even digits in x. And this number has how many even digits? 1, 2, 3, 4, 5. They're all even digits, so that value is 5. Here's another example. Here's another 5-digit number, 53,531. Again, it's a whole number, so I use the first part of the rule, the number of even digits. I count how many of these digits are even. 5's odd, 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 odd. There are no even digits, so the value of this function is 0. At this point. Now if I plug in a number that's not a whole number like this is not a whole number, then I use the otherwise part of the definition, and the function at that point is just 0. So we can use English to define a function, but you've got to be careful, right? Sometimes when you write down a definition of a function, you might write down something that's more ambiguous than you intended. So let's try to define a function, just making this stuff up. I'll call the function b of x for bad. And I'll say that the value of b of x is some rearrangement of the digits of x. And it's okay that I'm using English to define my functions. There's nothing wrong with that. But this definition is too ambiguous to be the definition of a function. Here's an example of what goes wrong. What's the function's value at 352? Well, the function takes its input and rearranges the digits somehow, right? So you might think that the function's value at 352 is 325, because 325 is some rearrangement of the digits of 352, right? I took the 5 and the 2, swapped their positions. But then the function's value at 352 should also be 235, because 235 is also a rearrangement of 352. The function's value at 352 should also be 532, because 532 is some rearrangement of the digits of 352. This is terrible, right? A function is supposed to take its input and produce unambiguously a single output value. But this so-called function takes this single input value and purportedly produces all these different possible outputs. This thing here is not a function, right? A function takes one input and produces one output.